Greetings, it's Paul Bamberg, and I'm going to work the sample problems for Class 1 of Math 117. This is my first venture with the new pad I just got, and we'll see how this scheme works out of putting the problems on the left, the solutions on the right. So, here's the first problem, getting you used to continuously compounded interest. Suppose you've won $1 million in the lottery, and this is going to be paid out over 14 years. You have three alternative schemes for collecting your money. The first one, you get half of it right away and can put it in the bank, but the other half you don't get until the full 14 years have elapsed. And then there are going to be two other options, getting 1/14 of the total at the start of each year, or getting this $1 million trickled into your bank account at a continuous rate over 14 years. So let's try the first one. This is the easiest. I'm going to assume an old-fashioned and currently rather unrealistic interest rate of 5%. And this is going to accumulate over 14 years. So let's first figure out what happens to the payment you get initially. You have $0.5 million, and that's going to get multiplied by the exponential factor e to the rn. That is going to be 0.5 times e to the 0.7. And it's worth remembering that e to the 0.7 is almost precisely 2. I put the exact number on the left-hand page. It's 2.0187. So the total is going to be 0.5 times 2.0187. That's your amount after 14 years for what you collect today. And then you get the other half, but you haven't accumulated any interest on that. That totals up to 0.5 times 3.0187. And that means you will have 14 years from now, $1.50935 million. Okay, let's try the second approach. In the second approach, you get a payment of 1/14 of $1 million at the start of every year, and that means you are going to have a total of 14 payments accumulating interest for different lengths of time. To be precise, you are going to get 1/14 million dollars multiplied by e to the r times 14 minus k. Think about this. The payment you get right away is going to accumulate interest for 14 years. K equals 1 is the payment you get a year from today, which is going to accumulate interest for only 13 years. And the last payment is going to be at the start of the 14th year. That will accumulate interest for 1 year. Okay, we can pull out a constant factor here. We've got a constant factor of e to the 14 times 0.05 over 14, and the rest is a geometric series. It's a geometric series with a ratio of e to the minus r, And the sum of that series, well, if it were summed all the way to infinity, we'd have 1 minus e to the minus r. But since we're summing only up through k equals 13, we have in the numerator 1 minus e to the minus 14r. Okay, this times 1 is e to the 0.7. This times this is 1. That's convenient. In the denominator, we have 14, and then I have to look up e to the minus r. I get 1 minus 0.95122. I threw this all into a calculator, and it worked out to 1.49162 million. Close to the first amount, but not quite as good. Now let's look at the third alternative. The third alternative is one where the money trickles into your bank account at a constant rate in such a way that $1 million will trickle in over the course of 14 years. So, if you have a payment after t years, the effect of interest is that it grows by a factor of e raised to the interest rate r times the amount of time that it has left to grow. If you make the payment after t years, it gets to grow for capital N minus t years, where n is equal to 14. And now, instead of summing, I integrate. I integrate over time from 0 to 14. The growth factor from continuously compounded interest, e to the r times n minus t, times the rate at which money is being paid in. That's 1 over n, where n equals 14. And I have e to the r n, that's a constant factor, over n. And then I have to integrate from 0 to n e to the minus rt dt. Well, that's an easy integral. E to the rn over n. The antiderivative of this is e to the minus rt divided by minus r. That's evaluated between the limits 0 and n. So I get e to the rn over n times 1 minus e to the minus rn over r. Again, multiplying out the numerator, I get e to the rn, which is e to the 0.7 minus 1. And this time I am dividing not by 14 times 1 minus r, but by 14 times r. So the only difference between the discrete case and the continuous case is here I have 1 minus e to the minus r. Here I have r, which is a very good approximation to this. And when I threw this into my calculator, I got 1.455285 million dollars. This is the worst of the alternatives, and it's fairly easy to see why the third alternative is worse than the second. In the second, you get all the money right at the start of each year. In the third case, it trickles in slowly. I haven't been able to come up with a good intuitive argument that says that the first alternative is the best of the three. Okay, let's move on to the next problem. So, bring up a new page. Bring up a new problem. And let's think about how to price a bond. Way back when, in the Carter administration, inflation was high and interest rates were correspondingly high. And interest rates of 10% were not uncommon. Municipalities were actually issuing bonds at a 10% rate, but you needed to get 10% back on your money because inflation was about 10%. Suppose one of these bonds is still around and it's going to mature in 5 years. It's making a payment of $1,000 per year, and it's going to do that right away and then at 1-year intervals until 5 payments have been made. And then, after 5 years have elapsed, the bond will mature and pay back its original $10,000 purchase price to the owner. Let's take a more realistic interest rate of 3% and try to figure out a fair price at which to purchase the bond. So first, let's think about the maturity payment and how much that is worth today. Well, you're going to get $10 million, but $10 million 5 years in the future is only worth $10,000 times e to the minus 5 years times the interest rate today. So I have to discount by a factor of 3% times 5 years. And when I threw this into my calculator, it turned out to be worth $8,607. The easy way to think about this is if someone gives you $8,607, you can put this in a bank account paying 3% continuously compounded interest. 5 years from now, that balance will have grown to $10,000. So this is the present day value of $10,000 5 years in the future. For the interest rate payments, each one is $1,000, and we have 5 of them. So for k equals 0, 1, 2, 3, and 4, we are going to have to discount by a factor of e to the minus rk. In other words, the payment that we get today has its full value. The payment k equals 1 has to be discounted by e to the minus 0.03 for the fact that you could have put money in the bank account and it would have grown over 1 year. And conveniently, when we sum these all up, we discover we just have to sum another geometric series. In the numerator, we have 1 minus the ratio in the geometric series, which is e to the minus r. In the numerator, we have 1 minus e to the minus 5 r. I take the data that I previously worked out on my calculator, and when I slap this into the calculator, the total present day value of these 5 future payments is $4,712 and change. It's a little bit less than $5,000 for the simple reason that getting $1,000 in the future is not as good as getting that $1,000 today if you can put your money in the bank and grow interest. And the total is the sum of these two, $13,319.40. There are a number of problems like this in the textbook, and in many cases the answer is given and the answer key is wrong. In one case, even the answer given in the errata sheet posted on the internet is wrong. These problems are a bit of a pain to work out, but we're going to be using this idea of discounting future values almost every day in this course. You might as well get used to it. Okay, enough for messy computations. Let's do a little something with exponentials. So, one way of approximating continuously compounded interest is to say, I'm going to break the year up into a large number n of equal pieces. In an individual piece of the year, $1 will grow to 1 plus r over n dollars, and this will happen n times. You may already know that the limit of this quantity as n approaches infinity is e to the r. I'm going to show you another way of looking at that. Because we can do a binomial expansion. When I multiply this out, I have the sum from I equals 0 to n of n choose I, that's n factorial over n minus I factorial times I factorial, and that is the coefficient of r over n raised to the ith power. Here's a clever way of rewriting that. I say n factorial over n minus I factorial is n times n minus 1 times n minus 2, and we have a total of I factors, of which the last is n minus I plus 1. We've got n powers of I in the denominator, n times n times n times this last n. What's left over? We have r to the I over I factorial. Now, I trust you recall that e to the r has the Taylor series expansion, sum from I equals 0 to infinity of r to the I over I factorial. That's sitting here. What about this other factor? Well, let's look at this. N over n is 1. N minus 1 over n is 1 minus 1 over n. N minus 2 over n is 1 minus 2 over n. There are only I of these terms, and the last one is 1 minus I minus 1 over n. And if we fix I and let n approach infinity, all of these terms are some finite number divided by n. Each of these factors has a limit of 1. The product of a finite number of them has the limit of 1. And all we have left is r to the I over I factorial. So for any individual term in the Taylor series, the limit, if we compound the interest n times instead of doing it continuously, comes out the same. Finally, here is the proof of the day. And this involves a trick for solving differential equations known as variation of parameters that you may or may not have heard of. What you're trying to do is pay off your student loan, and the way you're going to do this is you're going to extract money out of your bank account at a rate h of t. Could be constant, but it could be a function of time. So let's write the differential equation for the balance in your bank account. That balance is capital A. I'm going to use a convention that's popular with physicists and to some extent also with economists to put a dot over something to denote differentiation with respect to time. So this is the rate of change of the balance in your bank account. If the interest rate is R, the effect of that is to cause your bank balance to increase at a rate equal to the interest rate times the balance, but you're also taking money out of the account. So this is the differential equation that governs the growth of your bank balance. Now, here's the standard trick for solving this sort of equation when you've got only first derivatives and it's linear. No powers of A, no products involving A. The trick is first you solve the so-called homogeneous equation. F dot of t is equal to R times F of t. You figure out what would happen if you never took any money out of the account. Any solution to this equation will do, so I will use the solution F of t is equal to e to the RT. Any multiple of that will work equally well. Now is the tricky part. The trick is you set capital A of t equal to some new function, little a of t, times f of t. That is a of t e to the RT. Well, let's plug this into our equation. I'm differentiating a product, so I get two terms, a dot of t times e to the RT plus a of t times r e to the RT, and that equals r times capital A, which is little a, times e to the RT minus h of t. Bingo! This term and this term cancel. If that doesn't happen, you've done something wrong. It's this cancellation that makes the trick work, because now I can write down a formula for the time derivative of little a dot of t is equal to e to the minus RT times minus h of t. Now I integrate this from the present until the time capital T at which I want my loan to be paid off. And the integral of the time derivative of A is very simple. That's just little a of capital T minus little a of 0. But it's also equal to minus the integral of e to the minus RT h of t with respect to time. And I'm almost done, because at time t, my loan's going to be paid off, So a of capital T is 0. At time 0, e to the r times 0 is equal to 1, and therefore capital A of 0 is the same as little a of 0. And what have I concluded? Minus capital A of 0 is equal to minus the integral from 0 to t of e to the minus rt h of t dt, or if I drop the minus signs, the amount of my loan today has to equal the integral of e to the minus rt h of t dt. Now, I did that by solving a differential equation, but you can say this makes perfectly good economic sense. A payment of h in future money has to be discounted by a factor of e to the minus rt. One way of thinking of this, I could just take the money that's in my bank account today and use it to pay off the loan, or I could let it draw interest, increasing by a factor e to the rt, and then make that enlarged payment in the future. So you don't have to solve these differential equations. If you use this concept of discounted future values, you get exactly the same effect. Okay, that takes care of the 4 sample problems. You'll be doing some of these on your own. And now let me see if I can upload this to YouTube.